Okay, we're going to run through very briefly in this video. Firstly, types of load. Okay, so river carries three types of load. We went through this in the lesson today, so there shouldn't be anything particularly new. But we have bed load up here, and bed load is the larger particles moved by siltation and traction. And this is very important when you're talking about bed load, that you give a size. And according to our Hillstrom curve, boulders weigh in at about 500 millimeters in diameter and above. Number two then is suspended load, and these are the smaller particles held up, as it says here, by the flow. They tend to be a lot smaller, clays and silts of about 0.1 millimeters in diameter and below. And then finally, again we mentioned this today, the dissolved load. And these are soluble materials which are invisible to the naked eye, carried as chemical ions. So three types of load: bed load, suspended load, and dissolved load. We're going to think about velocity now of the water, and velocity is dependent upon three things. Firstly, the gradient, so the steeper the slope, it would make sense for water to flow faster. The discharge, the larger the discharge, then we tend to associate that with higher velocities. And finally, the one that we're really interested in, however, here are the channel characteristics, because 95% of a river's energy, approximately, is used to overcome friction between its bed and the banks. So if the channel can be smoother, less rough, and a particular shape, that will reduce that figure substantially and therefore make more energy available for work, i.e. transport and erosion. So two things we're going to run through here. We're going to run through firstly the shape of the channel, how that affects velocity, and secondly we're going to look at channel roughness. Channel shape. Okay, number one. This is represented by something called the hydraulic radius. Really important concept, this, the hydraulic radius. That is a measure of channel efficiency. Channel efficiency. And as we can see here, the higher or the larger the hydraulic radius, the more efficient the channel. Okay, efficiency being how much energy it loses through friction. And we can work out the hydraulic radius as so by taking the cross-sectional area of a channel and dividing it by something called the wetted perimeter. Now, the wetted perimeter, let's imagine here is our channel. Here is the water. Now, the wetted perimeter is the total length of the water which is in contact with the bed and the bank. So I'm just tracing out the wetted perimeter here. So that is the wetted perimeter for this channel. If, however, I add in a bit of bed load, and some rocks, the wetted perimeter will have increased, because now as I am tracing the wetted perimeter, it now follows the outline of everywhere that the water is in contact with bed, banks and bed load, and so the wetted perimeter of this channel is much higher. So going back to that concept, the larger the hydraulic radius, the more efficient the channel. And we've defined wetted perimeter as the total length of the bed and banks where the water is in contact. Now we're just going to think briefly about two different examples to illustrate hydraulic radius. So as we worked out, the hydraulic radius is the cross-sectional area over wetted perimeter, and with a large hydraulic radius we've got a smaller proportion of the water in contact with the wetted perimeter. Smooth, narrow, deep channels, such as this one, tend to have higher hydraulic radiuses than more shallow, broader ones. So if we draw two channels here, and we pop in the river in both, it is likely that this channel has the higher hydraulic radius than this one. So the more efficient channel is the narrower, deeper channel such as this one above. And just one final point is that a channel is at its most efficient when the river is at bankful level. So this is the most efficient. If the river level is above bankful, then we're in flood, and that means that there is very high friction. And if the river level is below bankful level, the proportion of the wetted perimeter relative to the cross-sectional area tends to be higher. So this is the most efficient at bank full capacity. Right, swiftly on to our second aspect. This is channel roughness, number 2. And channel roughness is can simply be thought of as how much friction is going to be caused between the water and irregularities in the riverbed and banks. So these irregularities might be, as illustrated in this photo down here, it might be to do with boulders, such as here. We can see in this channel, this is a pretty rough channel. There's lots of boulders and bed load, which is going to cause turbulence and friction. There is also some vegetation on the banks that's going to cause increased friction. And so this channel that we see in the photo is a particularly rough channel. But obviously the rougher the channel, the greater the friction tends to be, and so therefore the greater the amount of energy lost. Now we work out channel roughness by using something called Manning's coefficient of roughness. It's given the letter N. So it's a coefficient of roughness. Now, if we look down here to the table, we can see that we can attribute values to N depending on the type of bed. So is the bed uniform, i.e. flat? Is it undulating? Or is it irregular? Yep, like so. And so therefore, the more irregular the bed profile, the higher the value of N and the rougher the channel. We can see here that the roughest type of channel in this table is one of boulders and an irregular one, whereas a bed which has sand and gravel and is uniform in nature has a much lower value of N of 0.02. Now, the velocity, this equation here allows us to calculate velocity. So velocity is equal to, I'm just going to rewrite this because it hasn't come across very well, is the hydraulic radius r, down here, to the power of 2/3, multiplied by the channel gradient to the power of 1/3, all over this value of N. And so therefore, very simply, for you non-mathematicians out there, if the value of N gets bigger, then the value of V will decrease. And so therefore we can logically say that the rougher the channel, the lower the velocity, as more energy is lost to friction between the bed and the banks. Okay, is that clear? So the higher the value of N, the rougher the channel, the lower the value of V. Simple maths, if the dividing number or value is higher, the total value becomes lower. So the rougher the channel, the more energy is lost to friction and the lower the velocity. And so, in summary, what we can then wrap up with is that roughness decreases downstream. So as we move downstream, roughness decreases. Beds and the banks tend to get smoother. And so there is less friction as we move downstream. And this is evident in our type of flow. We tend to get more laminar flow the further downstream that we get. And so therefore, as we move downstream on a river, so down its long profile, velocity tends to increase as we move downstream, even though logic would state that the gradient is lower in the lower course. And so therefore we might think, well actually, so velocity should decrease with distance downstream. In fact it doesn't. Velocity increases downstream. And this is mainly to do with this factor of channel roughness. Yep. Roughness decreases downstream, and so therefore velocity actually increases despite the decrease in gradient.